Without further ado, I'll introduce our speaker today. So today, the speaker today is Elizabeth Cloud, who is a postdoctoral research fellow in the Penn Center for Learning Analytics at the University of Pennsylvania. She explores the role of affects on cognitive, metacognitive, and motivational processes that emerge during self-regulated learning, and its relation to learning and performance with education technologies and multimodal learning analytics. Her background is in psychology, learning sciences, education technology, and instructional design. And in 2021, Elizabeth completed her PhD in education and learning sciences. She was recently awarded the Marie Curie European Postdoctoral Fellowship at Temple University, which will be starting in the fall of 2023, and where her active and future research will leverage a multimodal mixed methods approach to study affect and the nonlinear dynamical system and study its relation to cognition and learning outcomes with a game-based learning environment. So today, Elizabeth will talk about theoretical, methodological, and analytical challenges, impeding our understanding of how to best identify and intervene if and when affect becomes detrimental during learning with education technologies. So I'm very excited. I hope you were too for this talk. And Elizabeth, thank you for being here. And please, the floor is yours. Thank you.
Thanks, Rogers. Thanks, everyone, for being here. I'm going to go ahead and dive in because we've got a lot of content to cover today in a short amount of time. And I want to start off this webinar by asking the following question. What is affect? And this is really important to think about and define because most of this webinar is going to focus on measuring and modeling affect. And affect is a pretty complicated, complex construct. So affect is an umbrella term that describes a feeling, mood, or an emotion that occurs during learning. And typically affect is multidimensional, and it's described as multidimensional by encompassing these multiple systems. And oftentimes these multiple systems, they can occur at multiple levels. And at these different levels, they can also occur at different timescales. So what I mean by this is depicted in the figure over here on the right. We can see that affect signals can occur at the neurobiological level. We can see chemical molecular signals can also occur at the psycho and physiological level, where we're seeing neuroendocrine, where the neuroendocrine system lives. We've got a lot of hormonal activity, heart rate, blood flow. We're also have signals occurring at the cognitive and motivational level. So we've got actions and behaviors occurring at this level. So all of these signals that are occurring within these different systems really emphasize its multidimensionality. And the function of these signals, typically within the context of learning, is that they serve to point out gaps in the learner's knowledge. And these are typically resulting from appraising events that can either occur internally or externally in the environment that relate to the student's values and the goals that they've set. So they're really these signals are to serve as functions that let the learner know how congruent and how aligned they are in meeting their learning goals. So a really good model, a theoretical model, I think that is based in psychological sciences that does a really great job of explaining and conceptually representing affect as this multidimensional space is the component process model built by Scher and others in 2001. And this model really breaks down affect into 5 emotion systems or components, as you can see over here on the right. You've got a cognitive component, a neurophysiological component, a motivational component, a motor expression component, and the subjective feeling of the emotion. And it suggests that all of these components are interrelated, and when there are synchronized changes that occur either within all of these systems or at least within most of the components, then that leads to the emergence of an emotion episode. And I really want to break this down conceptually in a better way by presenting the following figure. So we've got these 5 interrelated subsystems that are all connected. And within each subsystem, we've got a process that's emerging over time. And now when there are coordinated changes that occur between these processes within at least almost all of these subsystems at a micro level, then we've got the emergence of the emotion episode at the macro level. Now, to carry on with the rest of the webinar, in terms of educational research and its study of affect, a lot of traditional education has focused on measuring emotions. That facet of affect has dominated the space, and particularly understanding emotions as a unidimensional construct. And we typically refer to this as valence. So is the emotion desirable or undesirable? And we've come to know this as being a positive affective experience or a positive emotion, which we might think of as engagement within a learning context. In contrast, we might think of a negative emotion as being something like frustration or boredom, something that would impede a learning activity or gain from occurring. However, in the mid-2000s, there was this drive and push to have a more multi-dimensional understanding of emotions that occur during learning. And that recent model was published in 2012 by Sidney DeMello and Art Gracer, called the Model of Affective Dynamics. And this model conceptualizes emotions or affect as encompassing multiple dimensions here. And we can see that by its valence and by its temporality. So an important thing to note about this model is that the sequence of the particular emotion is really important. So to break it down for folks who are not as familiar, students who are engaging with information or trying to learn something, they should be engaging in information processing through engaged concentration. And now, as they're learning and engaging with the information, they may encounter an impasse in their understanding, something they don't understand. And so they could go down two paths. So they could go transition to a state of surprise, or they could transition to a state of confusion. And if that impasse is left unresolved, then they can transition into frustration and then eventually into boredom and complete disengagement. Now, in contrast to that, if the impasse is resolved and they are able to understand what they were missing, then confusion can transition back into engaged concentration, or it can transition from delight and then back into engaged concentration. And so this model has proposed a set of hypotheses that have really driven educational research on emotions over the last 5 to 10 years. And those leading hypotheses can be demonstrated here. We've got particular affect sequences that are hypothesized to be either beneficial or detrimental to learning. In the first affect sequence, we've got transitions from engagement to confusion to delight and back to engagement. That would signal that the student has resolved their source of confusion, and that should be beneficial for learning. Similarly, if we transition from confusion to delight, that ultimately means the confusion has been resolved, and that should be beneficial for learning. In contrast, when we see transitions from confusion to frustration, that may indicate that the impasse was not resolved and could likely be detrimental to learning. And similarly, when student transitions from frustration and then to boredom, that would also be detrimental to learning outcomes. And so again, over the last 5 to 10 years, this has driven a lot of empirical studies to test these hypotheses. And across the board, the empirical evidence does not match the theoretical model that we're seeing here. And in most cases, we're seeing the least clear results, or at least we have very little understanding of the role that confusion and frustration play in this particular sequence of emotions in regards to how it's beneficial or detrimental to learning. And in particular, we're seeing results where oftentimes there's a temporal component here that goes beyond the affective sequence, where the time in which the emotion is present, and if it's reoccurring or not, can have a beneficial or detrimental role to learning. So for example, if there are brief instances of confusion, sometimes that's beneficial and other times it's detrimental. So really teasing apart the dynamics of these two emotion states will be the ultimate narrative of the rest of the webinar today. And again, we may be seeing these mixed results due to methodological and analytical challenges in the field, where most researchers are relying on interval data. And interval data can be problematic because we're not capturing continuous signals of an affective or emotional state. So when we're relying on these interval data, we're capturing snapshots into the emotional experience. And typically these methods result from relying on interaction-based data to detect an affective state, or field observations or self-report measures. And while these methods are valid in detecting an emotion state, it draws the question of whether we can supplement those measures with more fine-grained continuous measures of emotions to capture all of the signals that may be occurring outside of that snapshot, and to capture multiple dimensions of the emotional experience, as we just discussed with the component process model. Now, the second set of challenges that could be contributing to these mixed results is the analytical methods that are used. So we need to find a way to dynamically model these very continuous signals of an emotion experience first, look at them linearly, but then also think about them non-linearly and multidimensionally to truly represent what an emotion episode is. And so to get at that, I'm going to present two leading questions, which will guide the rest of this webinar. First being, how do we measure affect as a dynamic process? And then the second being, how do we model affect as a dynamic process? And so for the rest of the webinar, I want to present two papers. The first is going to be a journal article that aims to address these two questions by measuring continuous streams of an emotion state, particularly focusing on confusion and frustration. And then I want to talk about a modeling technique we use to model a linear relationship here in a dynamic way. And then the second paper will discuss an interdisciplinary method we used as a sort of use case to test this new approach of applying a technique that will allow us to examine whether these emotions are acting in a nonlinear dynamic way. So let's get into the first paper. The first paper was just published last year. And in this paper, again, we tracked continuous streams of frustrated and confused facial expressions in addition to neutral expressions as sort of a comparison. What we wanted to do is we wanted to examine if there were dynamic linear relationships between the time that learners facially expressed frustration and confusion and time that they engaged in scientific reasoning. And we did so while they played with Crystal Island. Crystal Island is a game-based learning environment strategically designed to foster emotional engagement. So we thought this was really important medium to study these particular relationships. And it enhances that emotional engagement by introducing interactive game elements, and it also manipulates the learner's degree of agency. So when students are immersed in this environment, as you can see on the right-hand side, they may have a full reign over what actions they can take. So how often or in what sequence they can interact with different game elements, whereas students who have a more restricted level of agency in this game are not able to follow whatever path they'd like. They have to follow this very strict path of interaction, and it's designed to expose them to specific information that will be helpful for their learning. And so when learners were immersed in this environment, they were asked to solve this mysterious illness. So they had to go around the camp, this tropical remote island, collect clues on this pathogen. For example, they could talk to this non-player character here named Robert, who provided important information on bacteria. And then they could explore the rest of the island, and they had to generate hypotheses and then experimentally test those hypotheses in order to identify and solve the mystery and move on with the game. And so for this, we collected a sample of 78 undergraduates, and most of these students were not heavy gamers. And when they came to the lab, they were randomly assigned to one of three conditions. Now, I've already talked about the first condition being that full agency. We had 62 participants randomly assigned to that condition. And then we had 16 randomly assigned to the restricted agency condition. And then for the third condition, this was actually a no agency condition. So we didn't include participants in this condition because they actually didn't interact with the game-based elements. They actually watched someone else play the game in third person. So since that interactive component was really important part of how we define engagement, which I'll touch on in the next slide, we didn't include participants in that condition. And as you can see here, when they came to the lab, they were instrumented with multiple sensors. We have a facial expression camera here at the top of the computer, an eye tracker here at the bottom of the interface screen, and a physiological bracelet. And then we were capturing their online behavioral traces. And so to define the amount of time that students engaged in scientific reasoning, we relied on two data channels for this. The first being their eye gaze, and the second being their log-based, their log file interaction. So how are they interacting with those game elements where they were playing the game? And we broke up their actions into three different categories based on Clark and Dunbar's model of scientific discovery. And if you'd like more details on that, you can please refer to the publication down at the bottom here. Essentially, what we did is we broke up these action types based on the game elements. So if a student was reading books or research articles, that would be considered gathering information, part of the scientific reasoning process. Eventually, they could go on to generate hypotheses where they could collect items in their backpack or track their hypotheses on a diagnostic worksheet. And then finally, they could test those hypotheses by experimentally testing them with a scanner, or by tracking their final diagnosis sheet, which we would capture those interaction logs. And so every time the learner was engaging in these certain actions, we then referred to their eye gaze data. And we created areas of interest around these specific game elements so that we could capture alignment between the time they interacted with the game element and that their eye gaze was actually fixating on the game element. This would let us know for things, for instance, like were they reading the information, and this would let us know that they were actually engaged. So this was our outcome variable, and then we captured their facial expressions using a facial tracking system called eye motions. Now this system maps on action units to landmarks on the face here. So students are getting their landmarks mapped on, and then we're establishing a baseline by having students calibrate to the software before they played the game. What we did is we asked them to hold a neutral facial expression, and then the software calibrated this as their baseline. And so whenever while they were playing the game, if there are any deviations in their action units from that landmark baseline, then the configuration of those action units would determine if it was a confused facial expression or a frustrated one, as demonstrated on the right here. Now, if it was neutral, then that would simply indicate it was a baseline non-emotional expression. So to analyze relationships between these variables, we conducted a statistical analysis called a multi-level growth model. And we did this because we wanted to look at the linear trajectory of change in the amount of time that students were engaging in scientific reasoning. But we wanted to include multiple levels here because we wanted to account for between subject and within subject variability. And this model allowed us to do that by building a 2-level growth model. So at level 2, the highest level in the model, there was our sample of participants. So we had 78. And then within each individual at level 2, at level 1, we had their within game actions, which totaled almost 16,000 data points. And then we added several level 2 predictors, as you can see in our conditional model over here on the right. So we wanted to account for their level of prior knowledge, that might impact students' trajectory of engagement, scientific reasoning, and also that agency condition and action type. So we ran 3 separate models, one for frustration, one for confusion, and then one for the neutral facial expressions. And across the board, there are some really important findings I want to highlight here. So first, we've got emotion duration. So that duration of time that learners were facially expressing. We see positive significant relationships for frustration, confusion, and neutral expressions on the trajectory of engaging in scientific reasoning. Now, a second important finding is here in the pretest score. We're seeing that there is a negative relationship between prior knowledge and the trajectory of engaging in scientific reasoning, but only for the confused model. Now, this might suggest that confusion is moderating the relationship between prior knowledge and engagement. So this is an interesting result. Next, we see a positive significant relationship between that experimental condition, and specifically, the one denotes the restricted agency condition. So students who were assigned to the restricted agency condition had significantly longer trajectories of engaging in scientific reasoning, but only for frustrated and confused models, again, indicating a possible moderating relationship here. Now, this was specifically for our fixed effects. So this only accounts for the between subject variability. Now, when we look at random effects, we're accounting for within subject variability. So across the board, we're also seeing a positive significant relationship on the time that emotions are expressed with the trajectory of engagement in scientific reasoning for all 3 of our models. Interestingly, we're only seeing positive relationships for action types on the trajectory of scientific reasoning for confused. So this may also suggest that confusion is playing a moderating role on the action type, the amount of time the learner is engaging in that scientific reasoning within that action. Another important finding I want to note here is the R-squared. So we can see here that the R-squared for each of our models hovers above 85% into 90% territory. And this really means that our predictors are doing a really good job of explaining a variability in our outcome variables, that trajectory of engagement. However, a thing I want to note is that the fixed effects, so the between subject variability, is only explaining about 25%. So we're seeing that most of this variability that's explaining our outcome variable is coming at the within subject level. So this indicates that within subject variability is going to be really important for explaining how long someone is engaged in scientific reasoning. Now, some key takeaways from this model is that the more frustrated and confused students facially express those emotions predicted more time engaging in scientific reasoning. And one might argue that this is contradictory to Sidney DeMello and Art Gracer's model that affected dynamics. However, it is aligned with empirical results. We're seeing that sometimes more confusion and frustration does predict more engagement. Now, an interesting finding to note, again, was that within subject variability explained such a large proportion of that time engaging. And this might indicate that individual differences could be playing a really important role here and when a student decides to engage and continue re-engaging, such as their value system or the goals that they've set, their degree of motivation. Again, we also found that more prior knowledge a student had predicted less time engaging in scientific reasoning, and that this may be moderated by confusion. Now, for the next paper that I want to get into, I really want to expand on this work where we're looking at the linear relationship between confusion, frustration, and engagement. But I want to expand it in a way where we're thinking about emotion as a nonlinear dynamical system to sort of tease apart what different dynamics might look like and think about how the structure of the time series might play a role in how it impacts learning. So, in order to explain nonlinear dynamical systems, it requires talking about adaptive complex systems theory. And adaptive complex systems theory is an umbrella interdisciplinary framework that's used across a magnitude of disciplines. It's used a lot in physics and biological hard sciences. But in this particular case, we're going to focus on nonlinear systems. Now, nonlinear systems is interesting because it provides mathematical formulas that allow us to quantify changes in variables over time. So we can quantify the structure of a time series, such as whether that structure appears chaotic or unpredictable, or is it counterintuitive compared to more linear analyses. So this is how we'd like to extend this work. And specifically within this theory, we applied recurrence quantification analysis. Because this focuses on a single time series and the sequential organization of that time series. And I want to break this down a little bit. So this method, it quantifies the number and the duration of a recurrence in a dynamical system that's presented in this phase space trajectory. And it creates this phase space trajectory by using embedding parameters. So the first is that time delay. So it's infusing time in a single series, that single time series, and it superimposes that time series on itself. So we've got a y-axis time series and then an x-axis time series. And again, this high dimensional phase space trajectory reconstruction is a replication of the structure of the original time series. So what we're doing is we're just creating a higher dimensional space so that we can look at how the organization of change occurs over time. And we do that by creating another embedding parameter called a window scaling technique. And this window scaling technique just places a window of focus on a particular part of that phase space trajectory so that we can define when a recurrence might be occurring within that window. And we do so by defining the window of the recurrence using a radius. And you can see that the radius can be small here, capturing only a few particles, and extending to a lot larger, capturing many other particles. So as you can see, the choice of the size of that radius of that window is going to be really important and can have a huge influence on the trend that we're measuring. So for this particular use case, we applied this method on a sample of 80 participants. Now, we use the same experimental setup that I just described in the previous paper with Crystal Islands. Students were assigned to a random condition, that full and that restricted agency here. Now we have a different sample for this. So we've got 51 in this full agency condition and 29 in the restricted. Again, we didn't look at the no agency condition due to that lack of interaction. Then they completed a series of tasks. So we had them complete a pre-test, they were calibrated to the sensors, and they played the game. And then after, they completed a post-test so we could gauge their understanding of microbiology concepts. And so our research questions were around, do repetitive instances, so are there recurring rates of those confused facial expressions, and do they differ between those partial and full agency conditions? And then do those repetitive or recurring instances of those confused facial expressions, does that predict post-test scores while controlling for agency and prior knowledge? And so in our first research question, we set that radius to be a very small window because we weren't sure the extent to which, how big the window should be for such a granular time series. And to the best of our knowledge, this method has not been done with facial expressions data yet, specifically within the context of Crystal Island. So we set our radius very small to capture any nuanced recurrences. And then we calculated a t-test and we found no significant differences in that rate of repetition between the restricted and full agency conditions. You can see here that about students had recurring rates of confused facial expressions about 1.46% of the time of their learning session compared to about 1.5%. So this really indicates that they were expressing similar rates of repetitive confused facial expressions, regardless of their agency. And so I also wanted to provide a visualization of what this high dimensional space kind of looks like. So this is the recurrence plot. And you can see that this student has the lowest recurrence rate at about 0.89%. So you can see there isn't a lot going on here across this phase space trajectory. You can see that just by very little noise and boxes happening in comparison to the student with the highest recurrent rate at 3.65%. So we're seeing a little bit of recurrence here. We can see a little point here, here, and here, which may indicate recurrence. We've also got a little bit more going on here toward the end of learning session and at the beginning of the learning session compared to the middle. So just some qualitative insights from that. Now, for our final research question, we wanted to look at the extent to which those repetitive instances were related to post-test scores. And so we ran a multiple linear regression. And looking here, you can see that recurrence rate of confusion had a negative relationship with post-test scores. However, when we created an interaction term for recurrence rate and that agency condition, we saw a positive significant relationship with post-test scores. Now, this may indicate that recurrence rate of confusion is moderating the relationship between agency and learning outcomes here, because we're seeing that condition, specifically the restricted agency condition, originally had a negative relationship with post-test scores. But when thinking about the recurrence rate of confusion, then it seemed to flip that sign around. However, I do want to point out that our R-squared for this model was relatively low. It's only explaining about 35% of the variability in post-test scores. So this may indicate that the predictors we're using aren't explaining most of the variability in learning outcomes, possibly indicating that there may be other signals that we're missing here. And so a few key takeaways from this result is that the more recurring time that facial expressions of confusion recurring could be detrimental to learning outcomes, but maybe that relationship is flipped when we restrict the level of agency that the student has. Now, in order to move forward, another possible explanation for this result could be due to a very small window scale of that radius. And so what we're going to do in future work is we're going to increase that radius to produce a recurrence rate of about 2 to 5%, because that's the natural recurrence rate for human systems sort of in the wild. And so we'll see if maybe our window scale isn't capturing the recurrence at the right time scale here, or window rate here. So we can explore that a little bit deeper. And additionally, thinking about what other signals may be occurring that might suggest that confusion may be recurring, or there may be other aspects that we're missing here. And so I think this is where the utility of nonlinear dynamical systems can really be harnessed, thinking about measuring and modeling multiple dimensions of that emotion episode. And I think that calls us to think about this lovely figure again here. So thinking about these multiple dimensions, systems interacting macro level, giving rise to a macro level confused state. So when we think about what was just done, we focused on a single facet, a single dimension of emotion, that facial expression, and we examined it using autorecurrence analysis. Now, we're missing a lot of other dimensions of this emotion. So perhaps we can think about other analyses we can do with this by looking at 2 dimensions of a confused emotion episode. So thinking about the neurophysiological and facial expressive components, and using other analytical techniques based in nonlinear dynamical systems theory, such as co-occurrence network analysis or cross-recurrence analysis. And this would allow us to see if there are synchronies in between 2 different signals, the extent to which they synchronize in their detection of the presence of an emotion. For example, facial expression indicating presence of confusion. Well, what's the heart rate signal saying? And are they synchronized in some sort of way? Additionally, we can harness other methodologies that might capture all of the dimensions of the emotional experience. So thinking about more than 2 components, and this technique, this dynamical modeling technique, offers a way to do that. Particularly multidimensional recurrence quantification is one of my favorite techniques for looking at synchrony across multiple data channels. And this would allow us to start thinking about ways to merge more continuous data streams with more interval related data streams. So thinking about the validated measures that are already being used in education, and supplementing them and seeing the extent to which more fine-grained continuous signals are overlapping or merging with more large-scale signals like interaction-based affect detection. And so based on this discussion, that wraps things up. So if you want to scan these references, please do so using the QR code here. And I'd like to open the floor up for discussion and comments.
Thank you, Elizabeth. Give me 1 second to remove the spotlight. Right, so we can see everybody. Thank you very much for your presentation. Really interesting points. We already have some questions. And I think I would like to start with some clarifying questions first that we have here already. So you, Renee and Roger, you have very similar questions, 2 questions, very similar questions. Would one of you like to ask the question live?
I'd be happy to. So this is Roger. So I did some research with Sydney and Art several years ago, and it was before we had these techniques of some of the nonlinear stuff, so we struggled. But one of the things we found was boredom was, boredom was a key. So between frustration, confusion, and just boredom is like a disengagement. So there was that dynamic. I was wondering, did you decide it wasn't useful or just hard to measure for the newer stuff with Azevedo and I'm forgetting the other person, the guy who does Crystal Island, James.
Oh,
right?
James, yeah. Well, boredom was, again, we have limitations based on the tracking software. And I don't think boredom was an option in that way. And so we were only limited to frustration, confusion, but also we were really interested in these 2 particular emotions because they seem to define the point at which the emotional experience could be beneficial or detrimental to learning. And that the results overall were very mixed, and we wanted to really dive deep into the temporality here. And so that's mostly the motivation for why we focused on these 2 alone.
Okay, thank you.
Yuli, would you like to ask your question as I think it builds up a little bit on this one?
Yeah, thank you so much. So I have a question about the data analysis. You said that you have a system like emotion, or maybe you have also another system to predict the facial expression recognition. And then I'm going to know what is the raw data you get and how to convert to the statistical, so we can draw the conclusion if there is an effect on something to something. Thank you.
Thank you, Yuli. I just want to make sure I'm understanding your question. So your first question relates to which tracking system did we use, or which tracking system are we currently using?
In your slide, you use emotion, right?
Yes.
Yeah, so how to convert the raw data from emotion to the statistical, so we can gain the conclusion.
Yes, absolutely. Yeah, so iMotions is a facial tracking software that uses an algorithm that's trained on facial expressions, and it's trained on human coders coding facial expressions. So these algorithms are, they provide sort of like an estimate of the likelihood that an emotion is present. So when we got indication that the emotion was present, then we only included those data channels, and we removed all the remaining data channels that included emotion was not present. So it's kind of how our threshold was set. In addition, iMotions allows us to align the timestamps with interaction-based logs collected in a game-based learning environment, so that we could align the temporal detection of those facial expressions with the game-based interaction logs at a second level. And I hope that answers your question in terms of how we could dynamically model something like this. Awesome.
Thank you. Thank you.
Thank you.
Okay, thank you. Renee also had a question about the emotions that you selected in the experiment. which was thumbs up by 2 others. Renee, would you still like to ask your question? Are they still here?
Yes.
Yeah.
Sorry, I'm in a really quiet office space. I guess I was just wondering, have you looked into other type of emotions, or if you have like looked into research on, just how engagement, how the other type of emotions relate to engagement?
Oh, yeah, we haven't quite looked at engagement yet, but we are looking at this from a different lens. So thinking about facial expressions, for example, I want to go back to the facial tracking system, really determining what you're able to measure at the facial expression level. Currently, iMotions is no longer in capturing the same emotions that they were capturing 3 years ago. Now we've got basic emotions, so basic facial expressions, which are not confusion or frustrated states. And I'm not sure if they have engagement on there either, but I know they did at one point. So thinking about the multidimensionality of these constructs and facial expressions is, what are the underlying basic emotions that could be occurring between these different states? And could that inform when it's detrimental or beneficial to learning? So in terms of emotions, we haven't looked at other emotions beyond confusion and frustration, but we've been thinking about confusion and frustration as perhaps being a spectrum, right? And there's a lot of research around combustion and being around how do you distinguish emotions from one another and thinking about the multiple dimensions here. So that's kind of the space we're entering, and we haven't really gotten into the engagement space yet, but I imagine there's a lot more work that needs to be done.
That would be really interesting.
Absolutely.
And can I also just maybe follow up with the clarification? I think you talk about restricted agency conditions, and that's my other question. Like, could you clarify how you define that kind of condition?
Absolutely, yeah. Thanks for your question. So by restricted agency, these students were required to follow a specific golden path in the game, if you will. And so this golden path was designed to expose students to specific clues so that they didn't miss it. So this particular restricted agency condition was designed to enhance their scientific reasoning, whereas students who could have like full reign, full agency over whatever they did, we kind of hypothesized that they may be exposed to certain clues, but they'd have to figure that out for themselves and sort of do a self-initiated scientific reasoning. So I hope that explains the difference in the conditions there.
Yep. Thank you so much.
Thank you.
Yeah.
Great. We have one more question from Matthew, but before that, I have a follow-up question on this, because I was wondering how much can the confusion and frustration also come not necessarily from struggling with the scientific reasoning part, but with the game mechanics and figuring out how do I interact with this NPC, or how do I open my backpack and things like that.
That's interesting too, because I think that raises a question about the role of conflict. For example, there has to be I assume that, emotions arise based on some source of conflict, right? Especially particularly a negative emotion like confusion, confusion, uncertainty, a feeling of uncertainty and knowledge or something like that. So when it comes to a game mechanic and maybe learning how to interact with it, I could see that, being a different conflict compared to the more traditional, oh, I don't understand this information because I'm missing a knowledge, piece of knowledge. And so, yeah, that would be interesting. Would that be considered confusion in this context? I would ask. If it's not related to specifically information processing or learning information, then I'm not sure we would consider it confusion, but perhaps it could be related if the game element has information in it and they can't see it well, or yeah, I think that really gets muddled. And I think that's interesting though, because perhaps there are different sources of conflict and that could elicit different types of confusion or different intensity of confusion. It's kind of where I'm going with that. Yeah, that's interesting.
And how do you think you could detect that? Thinking of the facial expression, I think something else would need to be added on another data source, because confusion might look the same.
Yeah, absolutely. I think the facial expression should not be used. I think it should be supplemented. I think it should be used as a mean to supplement other data, for example, supplemented with interaction data, supplemented with even emote allows would be interesting. Maybe the student could disclose the conflict they're experiencing. Like, for example, I'm not understanding this piece of information versus I'm not understanding how to work this specific tool. And that maybe could provide a means to measure it. In addition, eye tracking might be helpful. Are they trying to read text, or are they looking at the game element and not able to figure it out? So I think perhaps we could measure it with multiple data channels here.
Okay, great. Then Matthew, would you like to ask your question? Okay, I could also read it out. So he wrote, I am curious as to whether or not there could be cultural variations of subjects as to how emotions are expressed and how that might influence the data set.
Yeah, I like this question a lot. This is really important to keep in mind that emotions are culturally influenced. For sure. And thinking about Western emotions versus Eastern emotions, the cultural differences likely play a role. I mean, culture determines, influences your value system, the goals that you set and you think are important during a learning activity. So the extent to which confusion or frustration might be elicited is likely dependent on that system. In addition, when we think about culture and expression, facial expressions, we also have to be really careful with using facial expressions of confusion or frustration, right? Because they're not universal emotions. And I think that's going to be really important for looking at basic facial expressions, basic emotions, which have a more foundational understanding of being more universal, at least theoretically, and has some empirical work. But again, there is some challenges where a lot of the basic emotion literature is based on one subset of a human being usually a white heterosexual male. And so we need to think about how are we training these algorithms, and then how might facial expressions vary by culture and values, et cetera.
Great, thank you. And then we have one more question, or two questions from Roger.
Oh, are you just going to read them, or you just want me to?
You can ask them if you're here and you would like to. Please go ahead.
Oh, so yeah, I was just there is some difference in some people like more. I don't want to know if confusing is the right word. Some like ambiguity. So some people are more tolerant of that and even looking forward to like taking something that's confusing or challenging. So I was wondering about individual differences on that, and then also. I was going to ask you about the mode aloud. I've done some stuff like that, and it can be really helpful for fine-grained analyses.
Thanks for your questions, Roger. The first one, let's see. I blanked when you said a mode aloud. I apologize. Confusion, individual differences. There it is. Yeah, feelings of uncertainty, feelings of complexity, feelings of novelty, feelings of familiarity, and that tolerance. Yeah, I could certainly see that. Individual differences would play a huge role there. Even your ability to recognize those feelings, I think would be really important. For some students may be unaware that they're feeling this way. And yeah, so the spectrum is there, that the variability and what elicits the strength of the emotion is going to be really reliant on those individual differences. And your second question, emote alouds. I've only done think alouds, but we are trying to start the study with emote alouds. So glad to hear that you had success with that, and it provided more granular indices there.
Yeah. So if I don't know, can I email you afterwards and I'll tell you about what we've done? Okay, great.
That'll be great, Roger. Thank you.
And then we have one final question in the chat from Vikaksono.
Oh, yes. Thanks. Thanks, Elizabeth. It's really nice to hear your presentation. So in the experiment, I noticed that you are using multimodality like camera and then eye tracker and physiological bracelet. So have you managed to integrate this physiological data into the model? And if so, which feature have you utilized and how is the result?
This is a great question. Yeah, thank you for that. This is where we hope to go next. So we're thinking of looking at heart rate because we can directly link the physiological measure of heart rate to polyvagal theory. And so this is how we're going to try to link it to the emergence of in relation to a facial expression and see how they may overlap or how they may one may lead into another, if you will. So looking at that structure is going to be really important. And that's the only study where we have facial expressions and physiology currently, but in the future, we hope to align emotolouds with physiology and facial expressions to sort of get at that, what's the ground truth and what did the other signals say?
Oh, okay, thanks. And what the device that you're planning to use in this bracelet?
Oh, the device we used an E4, the Empatica, I believe. And we've also used another one. If you send me an email, though, I can certainly send you the list. I think it depends on what you want to do, what you want to measure. It depends on what device you want to use.
Yeah, thank you.
Sure thing. Thanks.
Do we have any more questions or any thoughts or comments or ideas, suggestions from anyone in the audience? Renee, would you like to make that comment for everyone?
Well, it's just a random thought. I haven't read anything about that, but when you talk about the cultural aspect, I think it's just, yeah, it's interesting. I would just leave in a comment about that.
Yeah, I think that's interesting too, because the cultural aspect could really influence how you express the emotion. For example, is it appropriate to be frustrated in this particular context? And if individually, I would aim to suppress that if it was not appropriate. So that really does impact measurement and thinking about what other signals can we capture that might capture that potential suppression across cultures. Even thinking about gender is really important here too. Gender and race and sex, especially in terms of facial expression, detection, and the biases that are there. So even when we build these certain models, I think it's going to be really important moving forward to look at the degree of bias that may exist for different groups and think about how that may impact how we're detecting emotions. Are these models inherently more biased toward, females versus males, et cetera?
Great. Thank you. I guess Elizabeth is open for anybody who wants to reach out to her via email to continue these discussions. And if there are no more questions or comments, then I would hand it over to Isabel so we can wrap up this webinar today.
Thank you, Joanna. Well, we will now close the webinar, but we have posted first a link if you want to give us feedback about the webinar series. And also if you want to join Solar mailing list, you also have that link available. And after those quick announcements, I would like to thank Elizabeth for her presentation today. You can do virtual claps for her just on behalf of the audience. I see some claps there. Thank you. Great. And and also thank you, the audience, for joining us today. It has been a very inspiring discussion, and we will announce more details about the next webinar through our Solar newsletter. So that's why it's important that if you can join the newsletter, Solar newsletter, if you have not joined that newsletter yet. And also it will be announced in our social media, so feel free to follow us through Twitter and to be checking up our website. And we will leave the materials, both the recording and a description of the webinar in our Solar website. So thank you, everyone, and we hope to see you at a future webinar.